Welcome everyone to today's event on real-world applications of OLED technology presented by SGInnovate and Japan Science and Technology Agency, or JST for short. I'm Zing from SGInnovate, and if you're new to us, we are a government-owned organization from Singapore with the mission to build deep tech innovations from Singapore for the world. We invest in and help build deep tech startups in the fields of artificial intelligence, medtech, and quantum technology, just to name a few. We work with entrepreneurial scientists and clinicians to help bring their innovative research from lab to market, and we also develop tech talent and engage with a vibrant deep tech ecosystem. Today, SGInnovate is happy to collaborate with Japan Science and Technology Agency to bring to you the next in our joint deep tech series of talks by notable startups, researchers, and corporate innovators on OLED technology. Just some house rules. During the presentation, if you have any questions, please post them in the Q&A box at the bottom of your screen, and do feel free to use the chat box to connect with our wider community. Without further ado, I'd like to invite our friend and partner, Emi Kaneko, Director of Japan Science and Technology Agency in Singapore, to come on screen to share more before we start the presentations. Emi, please.
Thank you, Zane, for your kind introduction, and thank you everyone for attending today's seminar. JST is an innovative, mission-oriented funding agency, connecting a wide range of stakeholders and driving high-risk research that generates real value for global society. JST does a wide range of activities, but 65% of its budget goes in investment in basic research, and 22% to academia-industry collaboration, combination of which is about 106.4 billion Japanese yen, or 10 billion US dollars annually. Out of this amount, 33% goes to research in nanotechnology and materials. So this is certainly the area that JST or Japan is putting a big importance on. Today, I'm very pleased to co-organize this second seminar of our online series with our great partner, SGInnovate, together with our speakers from Japan, Taiwan, and Singapore. I'm very sure that they can unlock a door to the real-world applications of OLED technology for me and for all of you. Now, without further ado, let me introduce our first speaker, Dr. Junji Adachi, co-founder and CEO of Kyulux. He has over 30 years of experience as an engineer and manager at Panasonic before he moved to Kyushu University in 2010 as the head of strategic research planning, and then founded Kyulux in 2015. His talk title for today is Toward the Commercialization of Hyperfluorescence. Dr. Adachi, please go ahead.
Thank you very much, Amy, your kind introduction. My name is Junji Adachi, co-founder and CEO of Kyulux. I'll talk about towards the commercialization of hyperfluorescence. Let me share my screen. Okay, Kyulux was founded 5 years ago. We are the fabless manufacturer of TIDF, which is a emitting tech material for the OLED and for hyperfluorescence, with state-of-the-art AI materials informatics, which is introduced from Harvard University. Headquarters is located in Fukuoka, Japan, and we also have office in Boston, Massachusetts for AI material informatics development. We successfully raised 5 billion Japanese yen in Series A and B financing, and now we are in the Series B prime financing ongoing. As you can see here, LG Display, Samsung Display, Japan Display, OLED, and Sony are our strategic investors, along with JST and invested in us and from the Series A financing. So I used to work for the Panasonic, as Amy introduced me, and our co-founder and CFO, Akira Minakuchi, is an experienced venture capitalist, including 8.5 years in Silicon Valley. So after I met okay, Akira, he changed his career, okay, total investor to entrepreneur. CTO of the company is Hisashi Okada. He worked for Fujifilm and he initiated Fujifilm's OLED material business. But Fujifilm quit the business in 2012. Then he moved to Korea for Samsung displays for 3 years. And after coming back to Japan, he joined the company. Okay, and our business development side, and Sanyo Puyo is from LG Display, and R&D head led by Takahito Yamada. He worked for Pioneer as a OLED device development. And then we have two outside directors, Nicholas Braswell from WRVI Capital and Tsuyoshi Sakamoto from QB Capital in Japan. Our research team led by Chihaya Adachi. He is co-founder and world-leading researcher of OLED and the inventor of TADF and hyperfluorescence, along with Nakano Tani Sensei in Kyushu University and Kaji Sensei in Kyoto University. From the AI side, Professor Alan is a professor of University of Toronto. He developed our technology when he was in Harvard University. And Rafa is our collaborator for many, and he is an assistant professor of MIT. As you know, the OLED industry is growing very rapidly, and then now not only Korean manufacturers but also Chinese manufacturers get into the business and let rapid growth of the OLED industry. But the emission technology of the OLED still have issues. First and the second generation of OLED is called fluorescence and phosphorescence. Fluorescence has achieved very good all colors and low-cost material, but the efficiency is limited to up to 25% internal quantum efficiency. So in order to achieve this disadvantage, phosphorescence were invented, which is achieved under highly efficient 100% internal quantum efficiency by using iridium. But after 20 years of invention, deep blue is not available, and then the cost of the material is very expensive because of the iridium. So in order to improve the low efficiency of fluorescence, TADF was firstly demonstrated and demonstrated by Chihaya Adachi's research group in Kyushu University. By controlling triplet energy level, the energy successfully up-converted to singlet, then emit the 100% internal quantum efficiency without using iridium. But TADF has disadvantage about color purity because of the spectrum of the TADF is very wide. That means the purity is very low. So in order to improve TADF disadvantage, hyperfluorescence invented in Kyushu University, which is combined with TADF and fluorescent molecule. So TADF hyperfluorescence provide highly efficient, low-cost material, and deep blue is also available with high color purity. So this is a summarize of the relation of the emitting technology. As you can see here, only hyperfluorescence achieved all colors with highly efficient, low-cost material, and color purity is very high. Then, in order to achieve the same color purity by using phosphorescence and TADF, this part of the spectrum should be eliminated. That means exact practical efficiencies goes down. This is another benefit of hyperfluorescence. So this is a demonstration panel of the fluorescent and hyperfluorescence. As you can see here, the brightness of the hyperfluorescence is very high. So this color is the same color, but looks like white. So we control the camera and the exposure and the shutter speed. Then you can see the real color of the hyperfluorescence. It is the same color, but in this case, fluorescent is looks black because of the efficiency is so low. So this is a spectrum data of this one for fluorescent and hyperfluorescent. As you can see here, more than 4 times brighter than fluorescent achieved with very tight emission. This is a demonstration panel of the green, and this is a TADF, and this is hyperfluorescence. As you can see here, TADF looks yellowish green because the spectrum of the TADF including the yellow part. On the other hand, hyperfluorescence looks very pure green. So because the emission of the bottom emission here is very tight, and then when we apply the hyperfluorescence and the top emission device, as you can see here, emission light intensity is very high, and the spectrum is very narrow. Then we already achieved the ultra high definition TV requirement. This is a demonstration panel of the red hyperfluorescence using the same TADF molecule here. TADF, when TADF emit, it is an orangish yellow color, but when we apply the hyperfluorescent technology, all energy of the TADF converted to fluorescent molecule, then we can achieve the very pure red emission, as you can see here. So this is a summary of the benefit of the hyperfluorescence. Highly efficient, and then very low cost material. The all color RGB are achieved. So in order to commercialize our technology, we collaborate with all major panel makers in the world, including LG, Samsung, and Chinese manufacturers. And then in order to optimize the device structure, and we also collaborate with OLED material makers. And then we are going to outsource our whole large-scale synthesis of our TADF material. Once hyperfluorescence adapted in smartphone, smartphone will be higher resolution, brighter image, and 2/3 less power consumption. On the other hand, a large screen TV, this is the schematics of the structure of the OLED TV right now. LG display uses 2 layers of the blue emission because of the emission efficiency is very low. So we can achieve the reduce emission, blue emission from 2 to 1. Then the half the power consumption will be achieved and the huge cost reduction, both material and process. This is a material market expectations. As you can see here, the material market expected growing very rapidly. And then as you can see here, green and red part of the revenue of the dopant is very huge because of the phosphorescent material is very expensive. This is another motivation to replace phosphorescent to hyperfluorescence for panel maker. So we are going to replace current emitting technology to all of those to the hyperfluorescence, and then we'll be a dominant player of the industry. In order to accelerate the material development, we use AI materials informatics system, which is first introduced from Harvard University, and we add several functions from the original. So we call this system QMATIC. Consists of machine learning, quantum chemical calculation, experimental data management, and patent filing system to accelerate the development for more than 10 times faster. Then we already achieved the 10 times fast development speed, then going to expand our capability, not only molecule design, but also emissive layer design and OLED device design optimization as a whole in the future. So this is a world-first hyperfluorescence display, which is collaboration with Kyulux and WiseChip in Taiwan. Okay, and then we are very proud of this technology. We are available on the market right now. This is the current status of our achievement. Okay, we are developing yellow, red, green, and blue, and then as you can see here, okay, we achieved a very good long lifetime. Okay. So this is a progress of the lifetime, as you can see here. So yellow, red, and green are already achieved the target for the commercialization. And for blue, we are improving very much, and then we are going to achieve our target within a year. So this is a summary of our current status. Yellow is already commercialized, and red and green is very close to commercialization. We are going to get into the mass production test in next year. Okay, and then after 1 year of the green and red, blue will be commercialized. Okay, our technology is recognized as very high recognition. We got several awards from the world. And this is the summary. Thank you very much for your kind attention.
Okay, thank you, Dr. Adachi, for your very informative presentation. Now I'd like to invite questions from the attendees. And I asked Dr. Adachi to check the Q&A box with me. So the first question says to Adachi-san, what are your thoughts on QD-OLED implementation by SDC? Okay.
Okay. Okay, so let me change. Okay, just a moment, please. Yeah, actually, I have some slide for the benefit of hyperfluorescence. Okay. Then I can share my screen. Can you see here?
Yes.
Yes. So this is a schematic view of the QD OLED by Samsung display. Right now, they use blue OLED. Okay. Then green and red is color converted by quantum dots. In this case, since efficiency of the blue is low, so they use 3 layers of blue emission path. But once adopting hyperfluorescence, okay, they can reduce the layer 3 to 1. There is a huge benefit for the for this. We expect half or less the power consumption and huge cost reduction, both material and process as well.
Oh, it seems very environmentally friendly, right?
Yes, that's right.
Okay. Let me read the second question. Is there any plan that Japanese manufacturers such as GOLED or Japan Display to commercialize products using hyperfluorescence TM emission technology?
Yeah. Okay. As I mentioned, OLED and Japan Display is our investor, and then we are collaborating with them. Okay. So I hope that they also commercialize hyperfluorescence, because the OLED now is concentrated on the solution process manufacturing. Hyperfluorescence is also very applicable to their technology.
Okay, I suppose Japanese government is putting a lot of money in these manufacturers. So looking forward to a great, research outcome from these firms. Okay, I encourage the participants to, writing your questions in the Q&A box. We have until we have three more minutes for this Q&A for Adachi-san. So the third question, could you explain why blue OLED are lagging behind the other colors?
That's a very good question. Since blue light has a very high energy itself, then some of those organic molecule destroyed by blue emission light. But in fact, for fluorescent molecule, already commercialized deep blue fluorescent molecule. So we utilize this fluorescent molecule as emitter. Then we believe we can achieve the long enough lifetime for commercialization within the year.
Yeah, we all know that blue is a very important color, Okay. Okay, the next question. Amazing hyperfluorescence. Can the speaker elaborate a bit more on the mechanism of the emission?
Okay, so I also have some additional slides here. Then can you see this figure? Okay, so this is a schematic diagram and energy transfer diagram of the hyperfluorescence. Once on the green circle is a TIDF, and then the red circle is a fluorescent molecule. So fluorescent molecule can receive the energy from TIDF within first energy transfer radius here. So fluorescent molecule receive all energy from this TIDF molecule within the radius, then provide very pure color emission. This is another benefit of hyperfluorescence.
Okay. I think this is going to be one last question. I'm not sure if other sons are willing to answer this question, but the question reads: may I know the Kyulux approach differences with Cyanora?
Okay.
CINORE.
Yes.
Apologies if too sensitive.
Yeah. Cyanora is a German company, and then they first focusing on the TIDF or blue TIDF. But they recognized this is very difficult to achieve the deep blue. So they switch to the TIDF as emitter to hyperfluorescence. Actually speaking, Cyanora follows Kyulux, but the important thing is for IP. As you can see here, hyperfluorescence covers the basic patent, which is which Kyushu University owns, and the Kyulux is exclusive license from the Kyushu University. So this is a additional competitive advantage to Cyanora. Kyulux owns.
Okay.
In order to commercialize hyperfluorescence technology, this basic patent have to have. Okay. Yeah, thank you very much.
Okay, thank you very much. Unfortunately, because of the time constraint, we have to close this Q&A. Thank you very much, Dr. Adachi.
Thank you very much.
Yeah, thank you. Now it's time for us to welcome Dr. Chien Levy, Senior Assistant Vice President and OLED R&D Engineer Director, WiseChip Semiconductor Inc. He has more than 10 years experience with the OLED, and his expertise include OLED fluorescent, phosphorus material, and OLED devices. Before joining WiseChip Semiconductor, he was with Taiwan Semiconductor Manufacturing Company, or TSMC. His presentation title is Why WiseChip's PMOLED Provides You a Better Solution in Life. Dr. Chien, please go ahead.
Hi everyone, it's my great pleasure to have a talk here. I'm Alan Lee. My Chinese name is Li Jianle. I am R&D Senior Assistant Vice President in WiseChip. My topic is WiseChip's PMOLED provide you a better solution and life. Here is my agenda. First of all, I will introduce the WiseChip, my company's profile. And next, I will introduce you the WiseChip dominant position. As you know, WiseChip is a world-class manufacturer of PMOLED. Our strategy is to create a business environment that encourages innovations, open exchange of ideas, achievement of profitability, and growth with our customers. WiseChip was founded in November 2005. Our headquarters is in Zhunan, which is in the south of Hsinchu in Taiwan. Our capital is around the USD 70 million. Our chairman is Jackie Wang and the president is David Lee. Right now, WiseChip is the only names and produce the all PMOLED modules in Taiwan only. Our products are the market leader and the pioneer in the PMOLED, including the monocolors and area color, full color. We also sort them of function into character, graphic types, and icon types. We also accept some specific customized products. WiseChip can provide OLED module sales in different ways based on customer need, with shortest time and satisfy customers. We also issue the IPO in Taiwan's market stock exchanges on May 2015. Our stock course is 5245. In the beginning of WiseChip established, we make much effort to cost reduction to survive. After that, we start to improve our production to provide more quality and more quantities. We are qualified and receive all the certificates. Since the last 3 years, we start to develop new technology and new application, such as higher brightness and more visibility products. Our products are all required acquires Taiwan Excellence Award 2020. We also learn to satisfy our customer, transparency types, wide temperature range, series, bracelets, and hyperfluorescence PMOLED displays. The slides show our branch office. Our headquarters is located on Hsinchu, and we have 2 branch offices located on Shenzhen and Shanghai. In order to compete in today's global economies, we have distributors in the worldwide as shows, and spread our global reach to be close to our customers. WiseChip strive for serve our customer efficiency anytime. We can do every steps PMOLED process in-house in Taiwan. The slide shows we bought the ITO panels and do the laser mark, initial cleans, and photolithographic, OLED thin film deposition, in-cap, ink, scrubber break, and IC bondings. OLED can generate light themselves directly. It means that we have thinner, lighter, and better durabilities than LCD. We divide the better features into 4 parts. For electrical, it has lower power consumption and the driving at a low voltage around 4 volts, and it can be used as a wide temperature range from -60 degrees to 105 degrees. For mechanical parts, it is very thin to 0.3 mm and it is flexible and has slim border. At optical parts, it's fast response. It means that there is no image sticking and it can be transparent once. And while viewing angle larger than 170 degrees. High contrast 1000 to 1 and the sunlight readable. It also has good quality of long lifetime and lower defective rate. In advance, PMOLED is more simple structure than AMOLED. It means that we can quickly respond and has lower NRE fit and low MOQ when you want to apply the new models. Everything shows that PMOLED is the best embedded solution for you to be designed into your application. WiseChip want to keep the leading of the PMOLED. We focus on the new technology improvements, especially in flexibles and the transparent device. In our product roadmap, at the short terms, we keep improving the ultra-thin and the irregular shape, slim border products and provide the touch solutions, especially in TDDI, in-cells PMOLED. For the midterms, we produce more types and better curvable and even bendable flexible products. And we produce more application of transparent products, especially in optical ones. In 2019, WiseChip launched the 4th generation Hyperfluorescence OLED displays products, which is the first commercial product used its new generation organic materials in the world. The 4th Hyperfluorescence material not only has an advantage of cost, but also have highly compatible with mass production equipment. Optimize can rapidly introduce mass production and get ahead in the market. The newly hyperfluorescence OLED displays is simple but of marvelous character. For instance, the 2.7-inch 128 by 64 pixel arrays yellow hyperfluorescence OLED at the same power consumption can reach 220 nits. That is 2.5 bright better than the general fluorescence ones. Moreover, using this material also improves the lifetime of products more than 50,000 hours through optimize the structures. What is difference between the plastical and the glass types PMOLED? Actually, our flexible ones have almost the same advantage of glass PMOLED and have more advantage than glass ones, such as it can be curved right now and bendable soon. Besides, it has more light and things for you to adapt these kinds of displays. Our flexible product has a curvature less than the radius 20 mm, and it will be improved close to 5 mm soon. That's all people concern the reliability test about the flexible device. We notice the weakness and find out the difference between the customer designs. We have to do the reliability test at the curve statement because of the flexible device will be fixed at the curve stage and the edge area will be peeled off after long times. So we fine-tuning the lamination recipe and got the good results of the curve stage. Here are the results. We can reach the small radius to 20 millimeters, which is the smallest ones in the PMOLED manufacturers. We can see that after 24 hours at 60 degrees, 90% humidity reliability test, the pixel shrinkage at the edge less than 50%. Today, almost all applications are fit with the touch function. WiseChip launched the 1.3-inch TDDI OLED displays and won the Taiwan Excellence Award 2019 for its latest touch OLED display series products, which benefit is enable touch detections on existing display module structures. It is the thinner stack up of the PMOLED without laminations touch modules, and enhance the light transmittance and further improve the display quality by higher brightness, contrast ratio, and keep the same viewing angles. Currently, the TDDI module support 4 key ROMs and 4 button keys in a PMOLED display, or it can be designed into 8 button keys for some application. This gestures identification, single tap, double tap, long tap, and slide gestures, global operation, and wet finger operations. It also enables no force touch operation with water spreading at 2 cc water drop. Thus, great features make it possible and as the top embedded solution suitable for industry, medical, and smart application already. For the transparent ones, in our case of the transparent ones, we use the ultra-thin metal layer for our transparent conductive anode. We know that there was a trade-off between the transparency and the conductivities, which will affect the OLED device performance and the driving voltage. As shown in the right figures, we can see the ITO fin and the organic fin show the very high transmittance, around 19% at visible light wavelength range. And the receivers of 60 nanometer synchronous fins, the transmittance dramatically decreased with the wavelength to 40% only at 700 nanometer. For our case, we can see there are 2 types of transparency spectra we present. The mass transmittance could be better than 70%, and the spectra could adjust by optical cavity mode. These 2 different transmittance will be introduced to different outlooking device. The WSI-1 has a yellowish and the WSI-2 has bluish. We got the response that our customer like to bluish ones. These slides show the performance of transparent OLED. The right figures show current density, luminance, voltage characteristic of the TOLED white, green, and orange colors emitting. We can see the luminance for device have a lower threshold voltage and very high brightness, especially in orange colors. The luminance for the orange, green, and the white device reach 10 1000 nits with driving voltage only 2.7 volt, 3.7, and 6.6 volt. The voltage for the device are acceptable and lead to good device efficiency. This slide shows the lifetime of the transparency. The left features is accelerates the reliability about the results of drinking test at room temperature and at a current density of 200 milliamperes per centimeter square. And the brightness are around 30,000 to 40,000 nits. The luminous half-life LT50s of orange and the greens are around 280 hours and 220 hours, and the white colors is 360 hours, respectively. And we will get the predicted device lifetime at 1,000 nits around 21,000, 34,000, and 42,000 for each in this table. Besides, we improve our storage temperature more than 72 hours at 105 degrees C for automobile applications. What is the optical PMOLED can do? The most application is rifle scope, sporting scope, binoculars. There are some bright red for you to emit point. Besides, you can build in laser rangefinder together, which can allow you to range your target without carrying additional equipment. Further, because of wide range operation temperature from -40 to 85 degrees, we can hunt this at very cold environments, and you will not miss your target. These kind of products are very hot since last years. We have more than 10 customized products application now, and a lot of we are still talking to other customers. Another attractive application is our see-through display. We use it on the head-up display. This is a clear 180 degrees full viewing angles and the normal color distortions and the ultra-high luminance of 1500 nits that provide a clear and bright image to drivers and better information. We also can integrate the on-sale touch function for the better driving experience. In the future, WiseChip knows that PMOLED still has a growth market, especially in TDDI device, transparent one, and flexible applications. The smart function service market just opened, and the growth potential is still very big. PMOLED will play a very important role at the rapid growth. WiseChip will not miss the market and have a series of plans to achieve this great opportunity.
Excuse me, because of the time constraint, can I ask you to wrap up your presentation, please?
Yeah. Okay. So I think thank you for your listening. That's my old presentation.
Thank you very much. I'm very sorry for the attendees, but because of the time constraint, we cannot have the oral Q&A session for Dr. Jen Lee. But if you type in your questions in the Q&A box, I asked Dr. Jen Lee to type in his replies to your questions. Thank you very much. Do type in your questions for Dr. Jen Lee. Okay, now let me move on to our last speaker, last but not least. Let us welcome Dr. Young Lee. a scientist of Institute of Materials Research and Engineering, ISTA. She's now working in luminescence materials, flexible electronics, and smart biomedical sensors. She and her team aim to develop smart biomedical sensors for multiple biomarkers in sweat. In 2018, she was a SCRC Career Development Award recipient, and she's actively involved with the local materials research ecosystem. Her presentation title is Next Generation High Efficiency OLEDs, Novel Emission Mechanism and Device Architecture. Dr. Yang Lei, please.
All right, thank you. A very good morning to everyone who can join us this morning, and I thank the organizers as well for the opportunity to speak alongside such seasoned industry experts such as Adachi and Chien just now that we've heard. They are very wonderful technology and very wonderful talks. It's quite hard to follow up, but I will try and do a good job by speaking on something that's slightly more technical, slightly more academic, but nevertheless still grounded in real life application, in display applications. That's what we call use-inspired science, as we usually call it nowadays in A-Star. So my topic is on next generation high efficiency OLEDs, and I'm Le from the Institute of Materials Research and Engineering of A-Star. So let's move into the talk. Sorry, let me just. All right, the talk will be divided into roughly 3 parts. The first would be on the strategies to utilize triplet excitons, as we've heard a little bit from Junji Adachi's talk, that a lot of the efforts in developing high efficiency OLEDs, especially in the earlier years, has been on how to harvest these triplet excitons, which are the dark states. And in the first generation fluorescent OLEDs, they are like 75% of the system. So that caused the first generation fluorescent OLED to suffer from a very low internal quantum efficiency of 25%. So a lot of earlier efforts, very famous second generation mechanism phosphorescent back in the late 90s, and of course the all organic TADF system almost 10 years ago, championed by Chihaya Adachi, whose work I've always admired. And as we've heard from Junji Adachi's talk, it's very impactful. That's the third generation of the OLEDs. The third mechanism to utilize the triplets is triplet fusion. Is definitely less well known, less fancy, and less efficient, but nevertheless something that we shouldn't ignore completely, which I will allude to later on in the second part of the talk. But in the first part, I would like to highlight the spin state interconversion mechanism that my colleagues and I have developed a couple of years ago. So the second part of the talk is on enhancing conventional fluorescent OLEDs. And we've heard from Junji Adachi's talk that conventional fluorescent OLED emitters are still very important in display applications because of their stability, lifetime, the color purity, and the deep blueness that they can achieve. So there are 2 strategies here that I want to highlight. One is the dual dopant devices, and the other is that triplet fusion that I just mentioned. And lastly, before I end off the talk, I will mention of solution processing devices and this device architecture that we are quite proud of. So without further ado, let's jump right into this spin state interconversion, and we are illustrating this mechanism with our line of model materials. They are these linear carbene metal amides, or CMA complexes. And what happens here is that through an intramolecular rotation, it brings about a relative shift in the energies of the singlet and the triplet excitons. And at a certain critical angle, they actually cross each other. And at that point, the singlet and the triplets are completely degenerate. So basically, at that point, it's the most efficient at harvesting all the triplets into our devices as emissive states. Because at that point, the interconversion between the singlet and the triplet is extremely fast, and the reverse intersystem crossing rate is extremely high as well. So we've done a whole suite of photophysical measurements to prove prove the to support the mechanism. But of course, I'm not going to go through them here. We are more interested in real life applications in this event, and here we see the device performance. So we've managed to achieve a record external quantum efficiencies, record EQEs for these solution processable processed OLEDs at 27.5%. And as many of us know in the audience, that's equivalent to a near unity internal quantum efficiency, meaning that we are extracting all the excited states as emissive states in the device. So if you take a look at the EQE curve, the EQE roll-off at high current densities is very minimal. So that also indicates to us a near ideal device structure in this system. So bearing this mechanism in mind, let's move on to the second part of the talk on enhancing conventional fluorescent OLEDs for their uses in display tech. So the first approach or strategy is this dual dopant devices, making use of that CMA carbene metal amide complex that we mentioned just now, capable of doing spin state interconversion. So in this case, this dopant acts as the donor or the absorber of the system. The second dopant is the rubrene derivative TBRB. Many of us are familiar with. It's a yellow emissive compound, and it's this is the acceptor or acceptor or emitter in this case in this system. So energy would be transferred from the donor, from the CMA1 onto the rubrene derivative. So what we are seeing here now on the screen are the photophysical evidence of why we choose these two materials in the system, why we are doping these two together. We'll not go through all the details because it's a little bit more technical. And what I want to draw your attention to is this slide, this figure here at the bottom. It's illustrating all the processes happening in the system under optical excitation. So all the data that you're seeing on this slide are photoluminescence studies. They are under optical excitation. So a lot of processes are happening, but what we want to highlight is this number 5, energy transfer process. From our photophysical measurements, we are able to decipher that this step is extremely fast and extremely efficient. The time scale is sub-picosecond and the efficiency is more than 96%. So that how it's able to extract or suss out all the excited states from the CMA1 onto the rubrene derivative, and it can emit from there. So again, we are more interested in how they perform in devices, right? So let's look at what happens under electrical excitation, under electroluminescence. So the EL, the electroluminescence, as we can see here, comes completely from the rubrene itself, the rubrene derivative itself. There's nothing green, there's nothing coming from the CMA donor, which is green. And as we heard from Adachi just now, it's slightly narrower. The color purity is slightly narrower than undoped species. In terms of the device performance, we observe, again, very high EQEs, very high external quantum efficiencies of more than 20%. In this case, this should be the highest reported EQEs for this TBRB compound to date. And especially, it's especially important if you compare with the undoped device, just the TBRB alone, without the extra energy transfer mechanism, that's usually at best about 4%. So having the extra energy transfer assistance, it boosts the EQE by about 5-fold. So that's pretty good in enhancing normal fluorescent emitters. The EQE roll-off, as you can see at the higher current densities, is also reduced. This is plotted on a log scale, so the improvement that you see is actually quite a lot. It makes the device much better. It's able to achieve a much higher luminance, peak luminance. Of course, we know that in actual display applications, we don't need anywhere near as high a luminance. It's just to prove that it's a better performing device, and also that it can withstand high operational voltages in that way. So it dies less easily, basically. And in the figure here, the last figure here is a simple illustration of the processes happening in the system under electrical excitation in OLED, basically. And again, this energy transfer step is extremely fast and efficient, and that's how it can suss out all the emissive states from the CMA1 onto the rubrine derivative, and it can emit from there efficiently. So that's our first strategy. Moving on to the second strategy, the triplet fusion. Triplet fusion in OLED, it's better known as TTA up conversion, triplet annihilation up conversion in the optical TTA photon up conversion community. And basically, this is where two lower energy triplets come together, fuse together to form one higher energy singlet in this 2-to-1 ratio, and that singlet, as we know, it's emissive, so it emits from there. So and that way, it's a 2-for-1 harvesting of the triplets. In such a case, if we have a very perfect ideal scenario, we can calculate that the internal quantum efficiency limit to be at 62.5%, and that's extremely perfect ideal scenario. The range of emitters used are very similar. Many of them are very similar to what the optical TTA photon up conversion community are using. So in this case, for example, we chose four compounds ranging from blue to green to yellow to red across the whole spectrum to illustrate how this can be done. And we're trying to advocate the term fueleds to indicate OLEDs with this triplet fusion mechanism. So again, we want to see how they perform in devices. In this case, I'll just highlight one case study or one example from the yellow emitting rubrine device. So in this case, we are getting a peak EQE of about 40%. So a reminder that ideally, in the ideal case, that's 62.5% IQE compared to about 25% without any additional, 25% in the first generation fluorescent OLEDs. So that's pretty good. And we've done other photophysical transient electroluminescent measurements to indicate that in terms of triplet fusion contribution to the emission, it's nearly 55% contribution. So that's quite high, pushing towards the theoretical limit already. So that's a pretty good scenario happening in rubrine, and that's why we're highlighting this here. But apart from the yellow case, one thing that I would like to highlight is that, as you can see, we have a rather deep blue example here. So triplet fusion is intrinsically, organically, an energy up conversion mechanism. It intrinsically up converts lower triplet exciton energies into something higher. So that's extremely important in developing or designing more fluorescent emitters for deep blue display applications. Yeah, so that's the key thing I want to highlight there. That brings us to the last part of the talk, the last couple of slides, and this is where I would like to mention about solution processing of devices as compared to the normal vacuum deposition methods. So we completely recognize that vacuum deposition is in fact a mainstream commercial production technology. It's really versatile and precise, reproducible, very high performance devices obtained, and it's so widely adapted that it's almost impossible to challenge the current state of the art. The current typical solution processing method usually has quite a lot of disadvantages in terms of its poor performance, poor reproducibility, and the loss of control over the layers and the thicknesses and the interfaces. Now, so we also completely recognize that in the lab, our solution processing means a totally different thing from commercial production line, but we would like to address some of these disadvantages from our capabilities, and hopefully that can push for a better solution processing methods in the future. So that brings us to introducing in slightly more details our device structure that we're quite proud of. So this is a multi-layer device, and we've got very well controlled layer thicknesses and interfacial integrity. So for example, you see this device structure here. That's of course an example using the dual dopant device that we've heard just now. So in particular, if we choose our solvents used very carefully using, for example, Hansen solubility parameters, we are able to deposit a very thick layer of the whole transporting layer. And that's unreported before in literature. Usually people have very difficulty to increase the polymeric whole transporting layer because of the solvents chosen subsequently. So in this device architecture, every subsequent layer that we put down, it does not disrupt or wash away at all the underlying layers. That's why we are able to build it up like this. And in this case, we only need a very thin emissive layer, only 20 to 30 nanometers, which is quite thin for solution processed devices. And that's because we've got very balanced charges injected into the device. The balanced charges would all form excitons and recombine at this very thin emissive zone. So we've tested it for a whole range of emitters, both molecules and polymers, and it seems to be universally applicable. So a few examples are shown here, but we've got about 20 or 30, more than 20 or 30 emitters tested. We've all got very good performance in terms of EQEs and luminance. They are either comparable to or even better than vacuum deposited literature EQE values. So that hopefully provides some kind of springboard towards the next generation printable display tech, along with our mechanisms suggested just now earlier in the talk. And of course, it provides a platform to study the clean physics, because we know that without a reliable, well-performing device, it's very hard to study either the device physics or the material mechanisms. And with that, I will just conclude and recap my presentation. So we've gone through the three parts. Firstly, we've got the spin state interconversion, which led us to very high record EQE devices. There are two other strategies highlighted for enhancing conventional fluorescent OLEDs, and they are promising routes to designing, especially deep blue display pixels. And lastly, we've heard about the solution processing and the device architecture. So with that, I would like to end the talk. I'd like to thank the following people. I couldn't have achieved any of the both joy and scientific results that you've heard in the talk without them. From Cambridge, especially supervisor and colleagues and collaborators in East Anglia, and of course my current employer and scholarship provider, A-Star. Thank you. Okay,
thank you, Dr. Yang. It was a very informative presentation, which also echoed with the talks by the previous speakers. I think we have time for only one question. So that one is, would you be able to share on some use cases on this OLED enhancement?
Sure. Sorry, let me just look at the Q&A.
Yeah.
I'm trying to find the Q&A. Okay. Yeah. Yes. Would you like to share on some of the use cases for these OLED enhancement? So if, firstly, we constantly are looking for new solutions for high efficiency OLEDs because of energy efficiency primarily, and also currently one of the problems that hasn't been solved is the deep blue pixels in display tech, in in OLED display tech. So hopefully what we're suggesting are routes towards that. So that's one. And secondly is towards printable electronics. That's why we are developing these solution processable routes by choosing solvents carefully and designing architecture carefully. So, so I would say mainly these 2 or 3 points, which is always going for high efficiency, energy efficient display solutions. Second is the deep blue display problem, and the third is towards printable electronics. Yeah.
Okay, thank you for that. Can I ask you to type in replies to the other questions because of the
Yes,
we have
sure.
to close this session. Sorry for that. So thank you very much. And now I would like to give the floor to Chien for her closing remarks, please.
Yeah. Thank you so much, Junji, Chenle, and Yangle for the insightful presentations, and Emmy and the JST team for moderating and co-hosting the session. And thank you to all our attendees. I think we have about 88 to 90 who have stayed throughout the whole event. Thank you for your time and your questions. It's unfortunate that we don't have enough time to go through all the Q&A for both our presenters. We hope you have learned more about OLED technology from today's session. So just do mark your calendars for 23rd September 2020, as SGInnovate and Japan Science and Technology Agency will be having our 3rd event in this Deep Tech series on quantum technology. So do mark your calendars 23rd September. Do also connect with us on our various social media channels and keep an eye out for our post-event EDM with a link to the recording of the session, as well as if our speakers are okay with it, we'll also be linking ways to connect with them. We do hope to see you at future events and hope you have a great day ahead. Thank you. Bye-bye.